are going to do both this example and the main one in our text. So we'll do two examples for example 2. The reason we're going to do 2 is because the strategy for both of the examples is quite different. So I want you to see both of those. But what we're going to do in example 2, whereas in example 1 that we did the other day, we did a table of values to get some points to figure out what it was going to look like. And we used the end behavior, how it acted like a line or acted like a parabola to sort of figure out what it would look like. We're going to do the same thing here, but instead of just getting a bunch of points, we're going to use all of the intercepts. So the y-intercept, that's the one that's going to be the easiest to find because that's just plugging in 0 for x. And if you plug in 0 for x, sure enough, you get 0 as well. So we know that this graph goes through the point 0, 0. And that y-intercept happens to also be an x-intercept. Now to find our x-intercepts, we're going to want to factor. Now you got to be careful in this one because you see the x cubed and you might get tempted to do all of your factoring things that you did with x cubes before. However, in this case, there's a common factor here. We can factor out an x. And if we do that, that leaves us with x squared plus x minus 6. And we don't have to do any of that synthetic division or factor theorem or anything like that because we factored out a common factor. And then we can factor this further because x squared plus x minus 6 is x plus 3, x minus 2. So if we set y equal to 0, here I'll just write it out again. If we set y equal to 0, then we can find out everywhere that x could be that would make this equal to 0. So we have 3 x-intercepts. And it makes sense that the one x-intercept is 0 because that's the same as our y-intercept that we had above. So in order to sketch this graph using our intercepts, what we're going to do is we're going to plot all of our intercepts. So we have one x-intercept at -3, one at 0, and one at 2. We look at our original function. It's an x cubed function. The leading coefficient, the number in front of that x cubed, is a positive 1. So we know that the end behavior is going to act like a line. So once we have these 3 intercepts and we know that the end behavior is going to act like a line, we can draw a sketch. And all you're going to do is try to draw a smooth curve in between those points. And we've got our graph of our x cubed graph. What you don't know is how high does that maximum go, that local maximum, or how low does that local minimum go. So if you were asked the same question and you looked at your neighbor and your neighbor had this graph, you would both get full marks. Because based on the information that you have, you've drawn your intercepts correctly, you've got the end behavior correctly. We just don't know how high this point goes. If you wanted to get more accurate, you could do a table of values. You could plug in -2 and find out what it's equal to. You could plug in -1 and find out what it's equal to. But for a sketch, this is all they're looking for. Do you have your intercepts correct? Do you have the shape correct? And can you go from there? Now, the reason I wanted to do the one that is with the example as well we are going to do this one as well, is because this one does require that we use all of our skills for factoring in order to figure out. Again, so you don't have to write anything down here, you can just watch. I think the textbook has notes as well. I might do it a little bit differently, but first of all, I'd always start by finding my y-intercept since that's so easy to do. You plug in 0 for x and all of these first terms are going to be 0, and you just get that your y-intercept is -6. So as a point, you know that this graph is going to go through 0, -6. Now, as far as factoring this, remember, if you can factor this, then your factors, so if this can be factored to 4 things, whatever your last terms are in here, they have to multiply to get you -6. So your possibilities aren't that many numbers, because if you think about your factors of -6, well, that could be 1 and 6 or 2 and 3, positive or negative for any of those. So we don't have that many values that we have to check to see if it works. And the factor theorem and the remainder theorem says if I plug in a number, so if I plug in 1, then I'm going to get 2 times 1, which is 2, minus 1, minus 14, plus 19, minus 6, and this happens to be equal to 0. And since it's equal to 0, when we plugged in 1, this means that x minus 1 is a factor. And so we've already found one of the factors. As soon as you find one of the factors, you use synthetic division. So we're going to need to divide this initial polynomial. So it's already in the correct order, 2, -1, 14. There's no terms missing, so I don't have to add any zeros in my terms. And we're dividing by x minus 1, so we put a positive 1 out in front. Yes? It's a negative. Yes, thank you. That would have caused some problems. And we would have found out that problem when we get to our remainder, and it wouldn't have equaled 0. So right now, if things work out, we should get a remainder of 0 here at the end. That's what we're hoping for. So how do we do synthetic division? Bring the 2 down, multiply, add, multiply, add, multiply. Oops, it's positive 6, add. Sure enough, we get a remainder of 0. So now we can write our division statement, and this is where a lot of students lose marks on the final exam, is in the process of writing the division statement. We need to write an equation, and since it was already defined that f of x was the whole thing up above, it's really nice because you don't have to rewrite the 2x to the 4 minus x cubed minus 14x squared plus 19x minus 6, which takes up a lot of time. You can just write f of x equals, we know that our first factor was x minus 1, and we're left with 2x cubed plus x squared minus 13x plus 6. And what we're left with in our second one is still an x cubed. So now we look at, I need to factor this new one. I still have a 6 at the end. So I'm going to have to try plus or minus 1, plus or minus 6, plus or minus 2, and plus or minus 3 as well. And now I'm checking my new expression. So I'm going to, just so that I have new terms to work with, I'm going to define g of x to equal this part. That way I can show notation. So I tried 1 last time. Maybe 1 works again. So I try 1 again. 2 plus 1 minus 13 plus 6. Quick observation here. This doesn't equal 0. So I have to, so you say try 2. Thank you for looking ahead to save us some time. So 2 cubed is 8 times 2 is 16 plus 4 minus 26 plus 6. And sure enough, that equals 0. What does this mean? X minus 2 is a factor. And so now we can divide x minus 2 out of this. So we go to our synthetic division again. We had 2, 1, negative 13, 6. If we're dividing by x minus 2, a positive 2 would be out here. If everything works fine, this should be a 0 as a remainder in the end. We bring down the 2. Multiply, add, multiply, add, multiply, add. Sure enough, it works. Again, this is the point, the next line is where a lot of people make mistakes. So what am I trying to do? I'm trying to factor f of x. Right? That was my goal, was to factor f of x completely. I found one factor with the x minus 1. Then I created a new function g of x, so I could factor that, and now I found a factor of g of x, which is this whole thing right here. So I'm going to write that f of x, the original function, I already found out a factor was x minus 1. And when I factored that part that I underlined in a green pen, I found that x minus 2 was a factor of that, and what I was left with was 2x squared plus 5x minus 3. And finally, we've got something down to a quadratic. So if we want to, we can factor this completely. So we still have the x minus 1, the x minus 2. If this is factorable, it would be a 2x and an x. In order to get a plus 5, I need a 3 here. So my outside is 6. My inside is 1. I want a plus 6 minus 1. Quick mental math check to make sure my factoring works. My outside and my inside make plus 5x. The last ones make minus 3. The first ones make 2x squared. So it's good. Now we factored it completely. So if we want to find our x-intercepts, our x-intercepts is when this is equal to 0. Again, it's not bad to show that work. I know it takes time to write everything down, but it really, if you're working fast, doesn't take too much time. So we get 4 x-intercepts. Now, when we go to graph this, we use our x-intercepts and y-intercepts. So our x-intercepts at 1, 2, 1, 2, 3, 1 at positive 1, 1 at positive 2, 1 at positive a half, and 1 at negative 3. We know that our y-intercept was at positive 6 or negative 6? Negative 6, thank you. So those are our points, and just having those points is a little bit difficult to see what is it going to look like. In this case, we also have to think about this is an x to the 4 graph. It's an x to the 4 graph that's positive, so it's going to have the same end behavior as a positive parabola. That tells us we need to start over here. Go through this point, through this point, through this point, through this point, and up to end that way. Okay? Now, what I did here is very typical of what, when you have dots, you've trained from a very early age. When do you first do connect the dots? Like, is that grade 1, or do you have like even pre-kindergarten, your parents trying to teach you numbers, so they say, connect these dots together with straight lines and you will get a nice picture of a flamingo or something, who knows. So I did that, right? I went from, you see how I went from this point here to this point here? I almost tried to go straight there. In reality, this graph probably looks more like this. But we don't know where the minimum is. The red graph would not be marked wrong, okay? The only time the red graph would be marked wrong, and I was very close with my red graph being marked wrong, is in this section right here. So I'm going to just quickly, I'm going to show you a bad graph. Here, we'll do it in red again. So you're coming down, you want to go to this point, you're like, oh my goodness, I got to come back. Whew, I got a little crazy there. Well, this is not a function, because if I drew a vertical line test right here, it definitely goes through more than one point. That makes something not a function. And this is something you have to be careful with, because even sometimes when you're careful, you might come back just a little bit, and they will take off a half a mark for that. And so sometimes connecting the dots causes that problem, because you want to draw a smooth curve, and really the minimum is probably, in order to draw a smooth curve nicely between those, it's probably very likely that the minimum is quite a bit further down than what we see here. But again, you're not marked for not having the correct minimum. That's something that you learn in calculus. But you will be deducted if all of a sudden you loop back and don't make something a function. So by finding your x and y intercepts and knowing what the end behavior looks like, you're going to be able to draw a smooth curve through all those points and get a relatively accurate looking graph. So what we're going to do right now is we're going to take some time to try number 7 and number 13.